break, all right? So I think that is the end of, and so the output that you have here would be output that would allow, that came from the simple effects analysis using the using both method 1 and method 2. And so I don't have anything else to add to week 8, which we've been on for 3 weeks. So unless you have questions about ANOVA, one-way, ANOVA, two-way, post-hoc tests, we covered a lot of material. Questions? Are we good? Then I want to look at assignment 6 and then start talking about Manova, and we'll easily be able to finish this up next week, and then we'll be able to start on the final topic for class next week as well. When is assignment 6 due again?
15th.
The 15th. So no, is there an assignment due this Friday?
No.
Nothing due this Friday. Even though we're talking about this today, you'll be finishing this assignment or doing this assignment for a week from this Friday. All right. And so it should be the last page of the. I don't think I have it here, but I have the handout here. It should be the last page of the notes, and it's pretty straightforward. Use SPSS to perform a two-way Manova. So two-way meaning two independent variables, right? And you should have at least 3 dependent variables. So start thinking about your data. What would 3 dependent variables be that you have, and 2 independent variables, and one or more covariates, okay? So this is will require you, I think in most cases, you'll be able to use the data you've been using. There might be some exceptions, and if there are exceptions, we should talk sooner rather than later, and I'll help you find some data that you can use. But you need 3 dependent variables, 2 independent variables, and at least 1 covariate that you can put in the analysis, okay? So this is where I just said, instead of doing analysis of covariance assignment number 6 and this as assignment number 7, I just will add a covariate into assignment number 7. And it's pretty straightforward in terms of, the covariate part is very straightforward in terms of interpretation. In terms of write-up, it requires a line that indicates whether the covariates were significant and an F-test associated with that, and that would be about it. So there's not a whole lot to talk about in terms of the covariate. It's not all that much to add. Okay, so does that make sense? So that's, and then change, if you have it in front of you, or change your calendar and have it 11:15 instead of 11:14. Although if you want to have it in on the 14th, there'll be no problems. All right.
I didn't know you that we wait till the last minute.
Do you wait till the last minute? I don't think so. A lot of people have it done Tuesday or Wednesday. I shouldn't say a lot. Some people do. So
But you don't grade them till Saturday.
I don't even look at them unless it's just by accident until Saturday. So that's all I care about. All right. So that's assignment 6, the final assignment. And so now I want to talk about, we're going to spend the rest of the class period talking about Manova, and so multivariate analysis of variance and multivariate analysis of covariance. And I think Manova can be intimidating when you are first presented with it, but I think if you separate it into two pieces, which is sort of what we're going to be doing, there's really two pieces. One is what we've already done so far. It's just analysis of variance. And so we already know how to interpret analysis of variance, right? We've spent the last 3 weeks talking about one-way and two-way ANOVAs and interactions. So if you already know how to do that, you already know how to do at least 2/3 of the work in terms of interpreting Manova. The only difference is that there's a multivariate part that we add to the front end of the analysis. And that multivariate part is useful, but once we get, and it's once you sort of understand a little bit about what's going on, which we will over the next couple class periods, once you sort of understand a little bit about what's going on with the multivariate part, then everything else is exactly the same as if you were to run just single analysis of variance with as we've already done so far. Okay, so there's no other difference that that exists. It's just this front end that we add that helps us to understand at the multivariate level what's going on, and then once we get past that, the results would be exactly the same as if you were to run the individual analysis of variance. Everything is, the output is in a little bit different format, but in terms of sums of squares and degrees of freedoms and effect sizes and probability levels, it's all exactly the same. And so I think if you think about it in that way, that there's two pieces. One piece we already know pretty well, or hopefully you know pretty well. That's the ANOVA part. Now we're just going to add a little bit onto the front. And the way that SPSS handles Manova, at least by default, is the way that we're going to talk about ANOVA or Manova. But there's other ways to proceed past the multivariate level. So once you understand what's going on at the multivariate level, there would be a number of different ways that you could proceed in terms of understanding that. And we're going to just talk about the default way of doing that in SPSS, which is what I just talked about. So Manova at the multivariate level. So this is we're talking about what's happening at the multivariate level. It simply asks the question: is there a mean difference between groups on a combination of dependent variables? So what happens, and this is again behind the scenes, it's sort of the intuition or the way to think about what's going on behind the scenes, is that a new dependent variable is created as a part of the multivariate portion of the analysis. And the new dependent variable helps us to understand, are there differences across our groups based on this new combined dependent variable that gets made. And the best way to think about it, let's say we have 3 dependent variables that are a part of our Manova. What SPSS does is it combines those 3 together in a useful fashion, and by combining those together into a single variable, we're able to assess whether that variable differs across our groups. And if that newly created, behind the scene dependent variable differs across our groups, then it suggests that at the univariate level, there must be some significant differences across the ANOVAs that are going to be associated with each of the dependent variables. It really, what happens at the multivariate level, it's exactly the same as another statistical procedure called discriminant analysis. And in discriminant analysis, the grouping variable is the dependent variable. So your independent variables or variables that you traditionally treat as independent variables in ANOVA or Manova, they become the dependent variable, and your metric dependent variables would become the independent variables. And the question that we answer with discriminant analysis is, can we determine which group a person is in by their score on some dependent variable? And if we can determine which group somebody is in with chance, with greater than we'd expect to get by chance, we'd never be perfect at that ability, but if it's better than chance, if we can do that, then the logical conclusion to draw from that is that at the univariate level, there must be some differences between the independent variable or variables and the dependent variable. So we'll talk a little bit more about the multivariate portion of Manova, not getting into the mathematics behind it hardly at all, only sort of thinking about the intuition and how is it drawing the conclusions that it draws, and then from there, once we get past the multivariate part, again, we would then just move on and talk about the univariate ANOVAs and interpret those exactly the same as we've interpreted ANOVAs so far in this class. So some advantages, and then I have another slide with some disadvantages. With multiple dependent variables, you increase your chances of finding effects. And so assuming the dependent variables are theoretically meaningful, not just randomly collected and thrown together, assuming they're theoretically meaningful, including multiple dependent variables, would increase your chances of finding theoretically relevant, theoretically important findings. And then there is some protection against making type 1 error as a part of the multivariate portion of the analysis. Once we get to the univariate portion of the analysis, that protection is really not there. The protection comes at maybe we'll never get to the univariate portion of it, given the result of the multivariate portion of the analysis. So again, we'll think about this in two stages. We have a multivariate part of the analysis. Once we get past it, if we sort of get the green light to move past the multivariate portion of the analysis, then we'll look at the univariate part. The protection against making type 1 error rate only comes in play at the multivariate level, unless you incorporate Bonferroni's correction or some other correction in the univariate analysis that you do. Some people do, some people don't. There's not a way that it has to be done. Some disadvantages versus just doing several ANOVAs, because that would be the other option. You could run Manova, or you could just run 3 ANOVAs, one with each of your dependent variables, assuming you have 3 dependent variables. Or if you have 5 dependent variables, you'd run 5 ANOVAs. So what's the advantage? Those would be a couple advantages, but there is some disadvantages, more complex for sure to sort of interpret and understand what's going on at the multivariate level. There are some additional assumptions that need to be considered, mostly related to the relationship between the dependent variables, how strongly correlated are the dependent variables with each other. Outcomes can be ambiguous. Outcomes can be ambiguous because maybe you'll find significant multivariate effects for some element of the research or of the analysis, but then at the univariate level, you may only find a portion of those results are significant. And so even though at the multivariate level it appeared to be significant or appeared to be, the results appear to be robust, that might not be the case when you start drilling down and looking at the individual univariate results. And less power, greater likelihood of making type 2, or potentially making a type 2 error. So can somebody think of an example of research you've read recently, or research you've worked on, or research you've done, where you conducted Manova or Manova? Anybody have experience? There's a lot of people that, for example, those of you that knew Michael Fowl, never saw him do any other analysis besides Manova. Well, that's not quite true. His time that I was here with him, that's all I ever saw him do. His time when he wasn't here or when I didn't know him, I saw regression and, well, he did structural equation modeling too, so that's not fair. But he was a big, his default go-to statistical tool was Manova. He would do an inoculation study where they'd have 5 or 6 dependent variables that they cared about, and all of those dependent variables would nicely fit into a Manova with sometimes just one single independent variable, whether they were inoculated or not inoculated, maybe another independent variable in a few cases, and then covariates were usually the norm as well. So, and that was just really his. He just thought that was a better way to understand his data, and I mean, you can't really argue with. You can't really argue. Somebody else have an example of Manova, Mike?
We're putting together one right now for the NSF study, and our dependent variables are perceptions of credibility, attitudes towards ideological groups, likelihood of action. We have 5 dependent variables.
That's probably pretty typical.
Variables.
And so you're going to do a 3-way.
Manova, because we have a bunch of covariates too.
Right, and so that in that case you have 5 dependent variables, 3 independent variables, and then several covariates as well.
10 covariates.
Yeah, and so that very sophisticated analysis.
Yeah, I don't run the analysis.
Yeah, but it wouldn't be beyond. It's not, once you sort of get past, it's not all that complicated, to be honest. If you sort of just take it one step at a time. The couple hundred pages of output, though, for whatever reason, SPSS just spits out everything it can possibly think of, and Manova is really good at it. It gives you everything at least twice, and I think in some cases you get a lot of information a couple times. So that good example, probably perfectly appropriate. The other option would be to run 5 ANCOVAs, right? But a lot of reviewers might bristle at that. Why don't you run? I think that would be a natural reaction from a lot of people. Why run 5 separate ANOVAs? Why not run a single Manova or Manova? But the interesting thing that I find about that is, once you do the Manova part, you ultimately get to output that is exactly the same as the output you'd get if you ran the 5 and covas all by themselves. Exactly the same to the letter. And so there is some benefit in doing the Manova part, but it's not a magic bullet. It's not a cure-all. It doesn't fix all of the potential problems that we might run up against when we do multiple tests and increasing the likelihood of making an error. Anybody else have an example of a Manova that they've done or they read about recently?
I have a question.
Uh-huh.
The covariate is a continuous variable?
Yeah,
Or can
and
it
so
be anything?
if it's not continuous, it needs to be dummy coded. So if it's a grouping variable, you need to dummy code it so that it's just think about independent variables in regression and the same criteria would apply. Does that make sense? Are you thinking about variables that you can use for your
Well,
analysis?
where data is.
Yeah.
I'm
So-
just trying to figure it out.
The IR grant that we
Yeah.
already talked about, we would manipulate the game in duration, 60 minutes, 30 minutes,
Yeah.
and repetition, whether they repeated or didn't
Yeah.
repeat, and duration, repetition. Oh, and then another one, like single player versus multiplayer.
And so those are the independent variables?
Yeah, and then we would test for, mitigation of bias blind spot, mitigation of fundamental
Yeah,
attribution
yeah.
error, mitigation of,
Yeah.
and so, and then we had as many covariates as we did variables.
Yeah, and so that, again, it makes perfect sense given that all of the dependent variables are of interest. They're not duplication. They're different, in this case, clearly different types of biases that you're interested in assessing. It fits perfectly into Manova framework. So we can assess, just like in univariate ANOVA, we can have main effects and we can have interaction effects. If we, just to make let's say we have 3 independent variables in our analysis, similar to the example Michael talked about a minute ago. And the 3 independent variables were,
Supportive ideology, social consensus, and cognitive heuristics.
so in this case we have these 3 independent variables. How many interactions would we get with 3 independent variables? Do we still just get 1 interaction? You get all possible pair. You get 1 3-way interaction, which we won't talk about interpretation of 3-way interaction. It's very similar, but it's at just one other level that you have to get through before you can interpret 2 one-way or 2 interactions. But we'd have 1 3-way interaction, and then we'd have 3 2-way interactions. So if you do a 3-way ANOVA or 3-way Manova, you're going to get 1 3-way interaction, 1 interaction between IV1 and IV2, 1 between IV1 and 3, and 1 between 2 and 3. All possible pairs. Plus you'll get 3 main effects, 1 for each of your independent variables. And so you have a fair amount of results to comb through and hypothesize about and have research questions about, and an analysis like that could easily be, well, I've seen people make that almost a dissertation, or easily a journal article for sure. That there's enough here that you might have a hard time sort of compacting all that into a literature review that makes sense, and hypotheses and research questions. It might be difficult, but surely would be doable with somebody that knew the literature and was able to cut out what didn't need to be there. But so we'd be able to have main effects and interaction effects. We'd be able to assess, to some degree, the importance of the dependent variable or the group of dependent variable. Which of the which of the biases are best mitigated by playing the game in one of the couple conditions. You would be able to make some judgments about that. It'd be less definitive probably than some would like, but you'd be able to at least say, well, there are no effects for this dependent variable and this dependent variable. We found differences in several of the conditions or whatever it might be. You could assess for specific comparisons. Again, maybe you're not interested in all possible group comparisons or all possible interactions, but so you could just look at some specific comparisons. You can look at effects of covariance, and then it could be you can do repeated measures, just like you can do repeated measures ANOVA, which we haven't talked about. You could also do repeated measures Manova, and repeated measures would be meaning what? Repeated measures meaning
You measured it multiple time periods.
yeah, so time 1 and time 2, or time 1, time 2, time 3, and that requires a bit of different thinking about how to do the analysis and a different framework than the ANOVA that we talked about, although it fits into the GLM. But we'd be able to do that in a univariate context or in a multivariate context. So some practical issues. At very minimum, you need to have more cases than you have dependent variables in your analysis. That would be a very minimum. However, 20 cases per cell. So if you have a 2x3 analysis, you have 6 cells, and you would want 20 at minimum people per cell. And I'd be uncomfortable, I think, if it was just 20. That would be sort of like again, some floor of acceptability. And I would say as you add independent variables, so in the example that you used, Michael, I don't know how many different, but it might be 3x3x3, which is a lot of cells, or it might be 4x3x3.
We're doing 2x2x2x2.
I thought you only had 3 independent variables. So it's got to be 2x2x2 then. There's only a dimension for each level, for each independent variable. So 2x2x2, is that what it is? They all have 2 groups?
Yeah.
So it's just, you just have 2 times 2 times 2.
Yeah.
So you have 8 groups that you have to worry about. But it certainly could be 3x4x3 or some number, and that would have to be considered. Level of measurement of the independent variables can be any level that identifies groups, just like we had with ANOVA. The dependent variables should be a continuous scale, and the dependent variables should be normally distributed. If they're not normal, what might you do? If they're not normal, you might try to transform them in some way to improve the normality. And let's, because I don't think we've had this discussion yet, let's talk a little bit about independent variables in ANOVA. Let's say I have as an independent variable age, and I have spectrum from 18 through adult life, so 18 to, so all adults, 18 to maybe I have people in their 90s and people in their 100s. That's my independent variable. Would it be appropriate to use that variable as an independent variable in ANOVA? Why not?
We're not identifying groups.
So what could I do?
Transform it into like 10-year groups or something.
So you could say everybody in the young adults, and then we could do middle age, and then we could do elderly, and then we could do whatever is past elderly, or right. We'd come. That would be one way. That would be a way to do it for sure. And then that could become the independent variable. Is there a downside to doing that?
Like, what's the difference between some of these on the border?
Yeah, and so
They fall into like the 18 to 24 and they're 24
Right, so you're going to take the 25-year-old and say that he or she is middle-aged. And when the 18-year-old is young adult, right?
Yeah.
And so, and maybe 25, maybe it goes 25 to 45, middle age, right? Or something like that. Yeah, and so that would be one potential issue that the cutoffs are going to be arbitrary. And what else? What other? And I think that's it, Jack. What other problems might that cause when we take a variable that has this much range from 18 to 100, and we just collapse across all that data into 4 different groups? Yeah, it wouldn't be normal anymore. It would just be the groups. We wouldn't expect it to be normal. The distributions wouldn't be normal. No, I don't think so, but good try. What other problems? Yeah,
Isn't it difficult to transform it? Do we have to do it one by one? Because they're not in a group. We put numbers there. And when we transform it into interval measurement, it gives,
But we're taking interval level data and making it group level data, right? We're going the other way. We're taking age, which is interval or ratio, and we're making it into a grouping variable, right?
this is what I'm saying.
Okay? And so when
When
Yeah.
we have entered the ages like 5, 3, 18 or
yeah,
something,
yeah.
isn't difficult to then put them into groups? Doesn't take time?
We could get the machine to do it for us, like, right? Just say everybody in from 18 to 24 is going to be in group equals 1, right? And then everybody from 25 to 45 will be group equal 2. It could just be a recode. You could do recoding in SPSS. If you had to do it by hand, it might take a little bit. SPSS would do it for you, and you'd have it all done in 30 seconds. But let me take, what would be the issue? Is that a good practice?
No,
Why not?
because say you've got people who are baby boomers, and then you're putting them in with people who are hippies, right? They're different generations of people, and you just arbitrarily cut them
Right.
across.
Right, just like, right, and so that would be, we're throwing away information, right? We're assuming that everybody who's 25 to, say, 45 is the same, right? And everybody who from 18 to 24, they might be sort of alike, but I think that next, well, wherever you put, wouldn't matter where you put your breaks. You could put a break from 25 to, 35 every 10 years if you wanted to. And you still have the same problem with we're throwing away information about our respondents. And I don't think it's ever a good idea to throw away information. What would be the better approach?
Do a regression.
Yeah, so if you have a continuous variable as your independent variable, then don't be thinking about ANOVA. What happens if I have one independent variable that is a true grouping variable? Whether they were in the experimental condition 1, experimental condition 2, or the control group, and a continuous variable. Then what do? I have one case would work with ANOVA, one of the independent variables, the other independent variable, probably not so good with ANOVA. What would you do?
Call you.
What?
I'd call you.
No, you wouldn't. You wouldn't. You can figure this out.
Oh, no.
You can figure this out, or you wouldn't have to. What would you do? So the question is we have one independent variable that's a grouping variable, say political party identification, just to be consistent. We have another independent variable that's a continuous variable. Do we do ANOVA, or do we do regression? What approach would you take?
I would just do 2 separate. It makes sense to me.
Well, we need them together. We need to have
Why?
the interaction, or we care about the.
Can't you just use the age as a moderating variable? I don't understand.
You could pretend, but what analysis would you use? To have one grouping variable.
You use age as a covariate,
Yeah.
and then run the age
You could. What else? That would work. What else would you do? Another option. We talked about this already. When we talked about regression. What do we do with grouping variables with regression?
Oh, you can run them independently. You
We
can
do this thing. What do we do with nominal data in regression? Yeah. That's right. So we dummy code. So that would be the approach. So you have one continuous variable, say age. We have, which doesn't make sense to break it into groups and run ANOVA. We have one grouping variable, say, political party identification. We can't use that by itself in regression because it's nominal. So the approach would be to just dummy code up political party identification and then run multiple regressions without it. With our two independent variables, actually we'd have three independent variables, age, and two dummy coded variables for party identification. Remember how we dummy code variables? So that's something to keep in mind when we're thinking about ANOVA or Manova. And I would never throw away information about your participants and collapse across groups or collapse across the data to make groups. I would find another tool, another analytic approach to use as opposed to making groups. But it happens, we could pick up any journal and we find examples pretty easily of where people do that. I'm not sure why, maybe because they might have some logic behind it, but in some cases it just might be sort of a misunderstanding of what's going on. Couple more practical issues, independent observations. Again, just as a review, this will be the last time you get to see this. Unfortunately, or fortunately. Independent observations, again, are what?
I thought we just said that's what we use. The repeated measures analysis.
So repeated measures analysis would be a unique form of where the observations are definitely dependent. And so in that case, if we're doing repeated measures, Manova, this assumption is going to be violated. And that's perfectly fine because we're doing it in the framework of repeated measures. Let's assume we're not doing repeated measures. That was just an example of what one can do. Let's assume we're not going to do repeated measures.
So this is our assumption that we have independent observations.
Yeah.
That means like you couldn't do snowballing where you have 5 people, you have one person go out and find 5 people that can answer a survey.
Yeah, that potentially would be a violation of independence of observation. And so it's just the idea that there's no connection between responses. It's the most clear-cut way to think about it is just like when we flip coins. If I flip a coin, the first flip is completely independent of the second flip, right? What I get on the first flip has absolutely nothing to do with what I get on the second flip of the coin, right? And then absolutely nothing with what I get on the third flip of the coin. And that is independence of observation, sort of taken to an extreme that we can't get to in the social sciences because we are social beings and we do have connections, but we need to avoid the kind of clear potential pitfalls. Snowball sampling, having your class go out and get responses for you.
Can you call it random?
What's that?
Random sample.
Yeah, if you're randomly selecting people from the population, the observations are going to be independent. Yeah, and so I think that would be a good way to think about independence of observation. Is we're just randomly selecting individuals from a population. Although in our case, we aren't always able to randomly do that. For instance, when we have undergraduates participate in our research, Are we randomly selecting those people?
No.
No, they self-select to participate in our research. So that random selection component, but that doesn't mean that the just because they're not randomly selected doesn't mean that we're violating independence of observation.
But we assume that they represent the population.
No, I don't. I don't assume that undergraduates represent the population. If I'm doing an experimental study, I don't care that they don't represent the population either, right? I'm interested in the effects of some manipulation on some outcome of interest. And I'm not really, my goal isn't to generalize to some large population. I'm not answering your question very well.
Random samples are always independent observations, but independent observations are not always random.
Thank you, yeah. If it's randomly sampled, it's going to be very independent. But
Yeah.
not all, just because it's not randomly sampled doesn't mean it's not independently observed. Yeah. Make sense? So the book is actually inconsistent, and those of you, well, I guess I don't see many people. So chapter 7, in one place they clearly say that negatively related dependent variables are best, and then 20 pages later they clearly say that uncorrelated dependent variables are best. I was taught that the approach should be to look for or have dependent variables that are naturally inversely related with each other, because that helps with the Manova part where we're trying to discriminate group membership, where we're trying to predict whether somebody's in a group or not. But at the end of the day, smart people will debate with themselves about it in textbooks, and maybe not even because that's a fairly strong correlation, right? If the correlation is less than absolute 0.6, it really isn't going to cause too many problems. I think where you would run into problems is when you have, correlations. Let's say you have two dependent variables that are correlated 0.85. The correlation between two of your dependent variables the correlation is 0.85. What does that mean? The
They're
correlation,
measuring pretty much-
huh?
Pretty much the same thing.
Yeah, they're certainly measuring a lot of the same thing. And so I would suggest probably eliminating one of them. And but if you're keen on keeping both of them, you can certainly do that. But I think it should be pointed out as a potential limitation. And logically, it doesn't make a whole lot of sense to me anyway. If we have two things that are correlated at 0.85, again, even if you're calling them two different things, they likely are not all that different because the correlation is so strong. Does that make sense? Questions?
So
Yeah.
you should only fix strong positive correlations.
Refer to your textbook, yeah, because I say, and the textbook would confuse you as much as I would confuse. I would, to be honest, even if they were inversely related at 0.85 or 0.8, it would make me nervous because they're not doing all that much. They're moving up and down together more than they're not, and I think I could maybe redo this a little bit and include that. I think strongly inversely related.
Pretty much just like reverse coded.
Well,
Kind of
I said naturally occurring inversely related, which if you just reverse code something That's, if we reverse code age and correlate it with something else, that doesn't mean that two things are naturally, artificially. But I wouldn't get too hung up on this, given the difference that your textbook doesn't reconcile. This is just sort of from what I was taught. And then this point regarding is probably the more important of the slide. All right. So what we will end up doing is first determining if there's significant omnibus effects, we call them. And there's about 4 or maybe 5, I think 4 different tests that get done for each omnibus effect or overall effect. And we'll have to decide which of those tests do we want to use. We'll talk a little bit about whether we should use Wilks lambda or Fly's trace or one of the other 2 omnibus tests that are given to us. So that's the first thing we do. And there's an omnibus effect for every effect that we are assessing. So if we're doing a 2-way ANOVA, we have an omnibus effect for one of the main effects. We have an omnibus effect for the other main effect. We have an omnibus effect for the interaction. So we assess at the omnibus level what's going on with the relationship between our independent variables and dependent variables. If we have a 3-way ANOVA, we're going to have several more effects to assess. If we add covariates in, again, we'll have an effect for each of the covariates as well. But we make that determination. It's not a single number, but it's several numbers that we have to assess for each of the effects. And then if there are significant omnibus effects, we then have to drill down and look at the univariate results. That's the default procedure in SPSS. And we typically do this with just running an ANOVA for each of the dependent variables that we have in the analysis. Does that make sense? And so you might have significant, let's say we're doing 2-way Manova, and we have one of our main effects, there's no significant omnibus result for, but the other main effect, there is a significant omnibus effect for, and the interaction is not significant. If that's the case, which something like that could easily be the case, we only then examine the univariate results for that one significant effect. We're not if we're truly following the Manova framework, we really don't have the statistical justification to examine those other effects. And so we'll talk more about that and look at that in detail next Monday, okay? So is our homework due this Friday?
No.
Okay. I'll see you next Monday, if not before. And we'll continue here. And then I'll also put up notes for the final set of the final lecture. I'll get those up by the weekend, so we'll get to those next week as well. All right?
Next week's not our last lecture. No.
No, we're gonna. It's next week is finish this Manova and start on on mediation and moderation. And then the mediation and moderation lecture, as I see the schedule, is the last lecture. And then there's a week off, and you get an exam, and we don't have class for a week. And then we come back for a final exam during one of the class periods.
But we don't, okay. Yeah, the last 2 weeks in November, we don't have class. And then
Window? Yeah, that for the exam.
the last 2 weeks in November, we don't have class.
So that's like the
First week in
2
December.
weeks?
There's just 1 week off. If we have
Yeah, the
class
week of Thanksgiving, right?
We have class Thanksgiving week.
Oh, the week of NCA, that's what I meant.
Yeah, the
Week of
week.
Thanksgiving, we don't have class.
The week of NCA, we don't have class.
No.
We have class Thanksgiving week
We
and
don't,
NCA.
we don't have class Thanksgiving week. You said, it says no class, work on your take home.
So that's the week. Yeah, that's the week we have off. Yeah.
Yeah,
Okay.
but we have class the week of NCA.
So November
And then we come
18th
back
is
and it's the last week of classes.
Yeah.
November 18th is Thanksgiving week.
No, that's NCA.
25.
25th.
Yeah.
25th.
I can read these now. So when's NCA?
The 20th through the 24th.
Yeah. So the week of you guys will be leaving 2 weeks from now. Wednesday. So you can easily be here on Monday.
Yeah.
Let me shut this off quick before I forget.